For the Hutchinson model, we've seen that the equation of motion is m dot of t is equal to minus r m of t minus tau. Clearly, there's a fixed point at m equals 0. And the first thing we want to understand is the stability of this fixed point as a function of the time delay. So to keep the analysis simple, I'm just going to rely on geometric techniques. So let's begin by making the following assumption. Let's assume that if the time delay is short, that the exponential decay to the steady state that happens in the case of no time delay still holds. So let me assume that m of t is equal to e to the minus at, where a is yet to be determined. And so to figure out what's going to happen, let's take this assumption and substitute in the equation of motion. So if we do that, on the left-hand side we have m dot, so that's equal to minus a e to the minus at. And on the right-hand side, we have minus r e to the minus a t minus tau. So we can cancel an overall factor e to the minus at and the minus sign. And what we get from this is the following relation between a and the decay rate and the parameters of the system. A is equal to r e to the a tau. So this is a transcendental equation that we can't solve for A explicitly, but we can understand essentially everything that's going on by geometric techniques. What we do in this case is that we just plot the left and right-hand sides of the equation as a function of A and see whether or not a solution exists. So let's plot as a function of A the left-hand side and the right-hand side of this equation. The left-hand side is a straight line of slope 1. For tau equals 0, the right-hand side is a horizontal line, and there's a fixed point at r equals a. As we're going to see, there's a critical value of the time delay that gives rise to very different behavior. So let's call that critical value tau c. And so first, let's look in the region where tau is much, much less than tau c. And in that case, we can take our basic equation and we can expand it for small tau. And so we're going to get A is approximately equal to R, and then I do the first order Taylor expansion, 1 plus A tau. And solving for A, we get that A is equal to R, 1 minus R tau. So the solution increases as tau increases. And we can see that by looking now at the curve when tau is not equal to 0. So the right-hand side is growing exponentially with tau, and so what we'll have is something that looks like this. It's rising exponentially, and so it's going to cross the 45-degree line in two places. The lower crossing is the physical solution that sort of continuously maps to the solution for tau equals 0. This is an unphysical solution, and this is the case for tau less than tau c. The lower solution is what we found approximately by this Taylor series expansion. For tau greater than tau c, then what that means is that the exponential rise is so quick that we never cross the 45-degree line, and so there's no solution. So when tau is greater than tau c, there is no solution, no exponentially decaying solution. And finally, there is a critical value of tau, tau c, where the curve on the right-hand side just kisses the 45-degree line. This is a solution for tau equals tau c. So at tau equals tau c, there is two conditions that we have to satisfy. First of all, the right-hand side of the equation in the box has to equal a. That's a condition that there is an intersection. But we also need that the derivative of the right-hand side with respect to a is equal to 1 at the kissing point. So that means that the curve r e to the a tau comes tangent to the 45-degree line. So if we just do that simple algebra, we have r e to the a tau is equal to a. That's the first condition. And the second condition, if we differentiate with respect to a, we bring down a factor tau, so we get r tau e to the a tau is equal to 1. And if we divide these two equations by each other, we get tau c is equal to 1 over a. And now that we know what tau c is, we can plug it back into our original equation for a itself. A is equal to r e to the a tau, and evaluated at tau c, it says that a is equal to r times e, which is approximately equal to 2.718 r. The decay rate is getting larger as tau increases up to tau c. So the summary here is that for tau between 0 and tau c, we have that a increases, the decay rate increases from r 2.718r. And what this means is that there is progressively faster exponential decay as tau increases